solving linear recurrence relations. So here, in the previous unit, we guess, someone give us that magic formula. Remember that magic formula? We didn't derive it. Someone gave us that. Then we prove it. We use mathematical induction. But the problem is, if nobody gave us that formula, how can you do it? It's hard to guess, right? I don't think anyone can guess that formula. No way to guess. Golden ratio. How can anyone guess using the golden ratio? You cannot. Okay? So this unit, we need to derive it. We do not guess anything. We just find the solution. So, we need to do that. Solving linear. This is a linear. We don't have square anywhere, right? You have a square, that's too hard. Okay? So it's a linear recurrence relation. Okay? Equations. Yeah? And it is on this page, Appendix B. This technique on that. Okay? Do you remember in discrete math you have a section solving this equation? Do you remember that? Anyone? Because from the textbook, you have one section solving that. Do you still remember how to solve? Yeah, so I will, go through the whole thing. Yeah. But I'm thinking about, so I give you the technique how to solve it. Okay? I give you the technique how to solve it. Okay? The question is if you can repeat that, if you can use that technique to solve, if I give you a different equation, so if you can solve it. Okay? Yeah. All right. Let's recall in discrete math what we did in that course. Okay? This is called second order. Second, so you have two terms. Second order, one term first order. Okay? Now it's two terms. Second order, linear, homogeneous recurrence. Homogeneous. So why homogeneous? You don't have the constant term. If plus 1, you have a constant, then it's not homogeneous. Okay? Yeah. But now we don't have that constant term. So we have a homogeneous recurrence relation with constant coefficients. Okay? Coefficient 1, constant of coefficient. Okay? Not n. Okay? If we put n here, n minus 1 here, no, it's not constant. It's very hard. So we non-constant, too hard. Okay? So
it's homogeneous because you said the n values, why is it?
Homogeneous, that's, we don't have plus 1 term. Okay? Constant term, plus or minus any constant. If you have a constant, then it's not homogeneous. Okay? Now the constant terms gone, then we call homogeneous. Okay? Homogeneous, so basically each term same degree. Okay? Degree 1, degree 1, degree 1, that's homogeneous. Okay? If degree 2, okay? Square here, square here, square here, that's homogeneous. Okay? If square here, linear, it's not homogeneous. Okay? So every term you should have the same degree, then it's homogeneous. Yeah? Otherwise it's not. Okay? Yeah. All right. Good. All right. Oh, all right. So that's the general equation for this case. Okay? Yeah, general. Right? For our Fibonacci, because b cannot be 0. Otherwise, it will be degree 1. If b equals 0, you only have one term here. That's called degree 1 recurrence equation. Yeah. So not equal to 0. So we get degree order 2. So not degree 1. Order 1. Okay? Order 1. Second order. Order 2. Second order. All right. For our Fibonacci numbers, our a and b both equal to 1. So we need to solve this equation. Fibonacci number. Okay. All right, so let me leave to next time. Okay? The whole solution, yeah, we will do the next time. Okay. All right. Recurrence relation. We called, so remember, there is a long name for it, recurrence relation. So what kind of second order first? Second order, right? So you see two terms at the right-hand side. Second order, homogeneous, no constant term, and linear. So this is a linear equation, no square, right? Linear, okay? Linear. So we need to solve this type of recurrence relation. Okay, yeah. All right. So now let's try how to solve it. Yeah. Oh, just a minute. All right. Yeah. Yeah, because let me go back one slide. So what? Yeah, because it looks like. All right, so let's get to this point. Right, second. So we need to solve this. All right. Next, yeah, because we skipped one slide. Yeah, we should start here. Okay. Let's take a special view. The first step to get us started, that's very important. We need to explore the structure property. What is the structure do we have here? So that step, breakthrough step. Okay. All right. Consider a sequence. So let's consider, all these numbers, Fibonacci numbers, let's write as a sequence form. Yeah. We want to study this sequence. Can we use some special sequence to model the sequence? Model the sequence. Yeah. That imagination, important. Sometimes in problem solving, we need to use some imagination, very special imagination. Here, we use one. So what kind of imagination do we use? Let's guess the structure. Let's try to put something with the structure there and try to fit it. Okay? Here, this sequence, because we do not know much about this sequence. Let's try to use some special sequence to fit it. Okay? Yeah. All right, so here, this step, not easy to get it. We use a geometric sequence to fit it, to model it. This step, yeah. How do you know the geometric sequence, right? Here, yeah. So mathematicians, they just try different ways, okay? Mathematicians at this situation, they just try various ways, see which one works. Here, the geometric sequence would work. Yeah, let's see, how does it work? Geometric sequence. Okay? So people just, is it possible we just make AK equals T to the kth power? Is it possible? It looks like no reason why you assume that. No reason. We just want to see if a geometric sequence can fit into this recurrence relation. That's it. We want to see if there is any geometric sequence that can fit in this recurrence relation. That simple. Okay? Yeah. If it's possible, then we have a chance. That simple. Okay? All right. Now, let's ignore the initial conditions. Initial condition, we will fix it later. Okay? So initial condition, yeah. Do not worry at this point. Yeah. Question, can we find a solution with this structure? That's easy. Let's just plug in and see what happens. We need to solve this equation if we plug in. Okay? After cancellation, simplification, we get t squared equals t plus 1. We are familiar with this quadratic equation, right? Yeah. Can you cancel out t to the k minus 2 power both sides? Do cancellation, right? So divided by this 1 t squared. Yeah, cancellation. Okay? Yeah. This quadratic equation, we solve it several times, right? Yeah. So we know the solution. Quadratic formula, remember? Golden ratio, right? Yeah. So we have these two solutions, T1, T2, two solutions. So we're familiar with this step. All right. Okay. There are two solutions here. Remember, in our last time when we calculate Fibonacci numbers, we drop one of the two solutions, right? Should we, when we calculate the golden ratio last time, we drop the negative solution, right? Here, should we drop the negative solution? Here, do we have any reason to drop that negative solution? No. Yeah. Golden ratio cannot be negative, but here, what is the t? Here, our t, it's not golden ratio. It's not a ratio of two line segments, right? We don't have that meaning. So t could be a negative number. It is allowed to have negative number here. So we have two solutions. Don't drop anyone. Don't drop anyone. Two solutions. So we keep these two solutions. All right. So let's continue using these two solutions. All right. We know both two solutions won't satisfy the initial conditions. We know because they're integers. Non-integers, how can you fit it? Right? You cannot fit initial conditions. So don't worry. Yeah. Don't worry. So we have chance. Now, from special solutions to general solutions. Those T1, T2, we have two special solutions. Okay? Two special solutions without satisfying initial condition. That's our description. No initial condition. Without. Okay? Two special solutions. All right. Now we want to write a general solution. There's another important step. From two special solutions, we want to write a general solution or more general solution. Okay? Yeah. Let's see, how should we do it? Okay. So we have two special solutions. Remember geometric sequence. This number to the kth power and that number to the kth power. Two geometric sequences satisfy this both, that recurrence relation. Okay. All right. Specifically, T1, if we plug in, we have that. Okay? Because we solve it from there. Okay? And T2, if we plug in, we also have that solution. Okay? Two special solutions. Okay. All right. Can you form a more general solution from these two special solutions? Okay. We use these two special solutions as our building blocks to construct a more general solution. That's an important step. Okay? All right. Yeah. After we get a general solution, then we can consider how to make it satisfy the initial condition. Yeah. So we need to get a general solution. Then we worry about initial condition. Okay? All right. So that general solution. How to use two special solutions without the initial condition to get new solution with the initial condition. That's what we want to do. Our plan. Next step. We want to do this. This question.
You said it equal to 0 and 1, and it's now in the self end.
that won't work, right? That won't work. Yeah. You need to get a general solution first. Then you have chance. Okay? Yeah. So that's why that step is critical. Yeah. All right. Use linear combination to form solutions. Linear combination. Okay. Let's try to get some property, observation. The property of the structure here, recurrence structure here. Okay. Here, there is one simple property that is very useful. Remember, I mentioned that at the beginning, we said this recurrence relation is a linear recurrence, right? We said that, linear. That linear is the property, right? Linear property. How do we take advantage of this linear property? Linear, okay? Linearity, this property, will be very useful here. Linearity, okay? What's that? This is a linear recurrence relation. How to take advantage of this linearity property? Yeah, okay? Linear combination. Do you know this concept, linear combination concept? You don't have this linear combination concept. Yeah, we need that. Linear combination concept. Okay. Do you have, yeah, some of you, I hope some of you took linear algebra 2450? Do you have that concept, 2450, linear combination? Yeah, not input output. Give you a vectors. Now you use linear combination to form another vector. Do you have that idea? Linear combination to form another vector from given vectors. Here, we change vectors to variables. Okay? Two solutions. Yeah, two solutions. You can treat two solutions as two variables. Okay? Can you do linear combination of two solutions? Things like that. Okay? So here, let me review this concept, linear combination concept. Linear combination of two variables, x and y. What's that? It is ax plus by. A, b are coefficients, constant coefficients. Any constant, we can use a and b. So we call this structure linear combination structure. Okay? So here, when we construct that special solution, we use, not special solution, general solution, we will use the linear combination of two special solutions. Okay? X is our special solution number 1. Y is our special solution number 2. Now we do linear combination of those two special solutions. For any constant A and B, we claim that will be a new solution. Do you believe that? Any A and B, ax plus by will be a new solution? Can you imagine that? Right? This is an important step. Yeah, try to get that. Okay? All right. So, new form of a solution. Now I write that new form of the general solution. A times first solution plus B times second solution. Can you see this new expression will be another solution of this equation? Can you get that? Any doubt? Do you need me explain it? Do you need me explain it? Why it is a new solution? Okay.
Doesn't hurt.
Oh, doesn't hurt. Good. Yeah. But I do not need long. 1 minute should be enough. Okay. 1 minute. Okay. All right. All right, so let's do here. All right. First solution. You know this is the first, oh, sorry. Yeah. Yeah, it took me some. You know this is the first solution. Okay? You also know this is the second solution. Right? No problem. At this step, right? Now, let's do some algebra. Okay? Equivalent transform. Okay? Equivalent transform. Okay? For the first equality, can I multiply a non-zero constant both sides? Right? So how about I multiply A both sides? For equation B, how about I multiply B both sides? B constant. Okay? So B. Can I add up two equalities? Add up two. The left-hand side, is that our new form of a general solution? A, yeah, so let me write fast away. That is A T1 nth power, right? Plus B T2 nth power, right? Equals A T1 n minus 1 B T2 n minus 1 plus A T1 n minus 2 plus B T2 n minus 2. Okay? Can we treat as a new solution AN? This AN minus 1, that AN minus 2. Is that the, it satisfies the recurrence relation? And, AB can be any constant. AB, any constant. 1, 2, square root 5, pi, e, log, any number. It would work. Okay? All right. That means we have freedom to choose A and B, right? We have freedom to choose A and B. Two freedoms to choose. Can we choose appropriate A and B to make it satisfy the initial condition? We have an initial condition to be satisfied, right? Here, because we have freedom to choose A and B. So we can choose appropriate A and B to make the initial condition satisfied. Then we solve it. Okay. All right, so let's see. How do we choose the A and B for the initial condition? All right, so let's go to the next slide. All right, now we are ready to fix the initial condition for suitable A and B. Last step. The goal, determine the coefficients A and B. Okay? Yeah. Such that the initial condition is satisfied. Okay? Yeah. Now you can plug in a number. Yeah. So let's denote AN equals that expression. Okay? A0, what is A0? Okay? A0 equals 0. Let's plug in 0. 0. What's that? Okay? When n equals 0, 0th power, 0th power, 1, right? 1 times A, 1 times B, That is A plus B. A plus B equals 0. Okay? A plus B should be 0 to make this A0 equals 0 satisfied. Yeah. Then second one. Okay? Let's plug in 1. Okay? Let's plug in 1. Oh, sorry. Yeah. N equals 1. We have this equation. Okay? All right. Now, so I hope you do not get scared by, complex parentheses, root 5, because let's solve in this way. Because A plus B equals 0, this is 1. That means B equals negative A. Okay? B equals negative A. Can we replace this B by negative A? No. Let's replace B by negative A. Okay? So we can factor that A out. Then the first parenthesis minus the second parenthesis. So we can simplify it. Right? So we get square root 5 times A equals 1. Root 5 times A equals 1. So we can find A equals 1 over root 5. A, 1 over root 5. B equals negative A, right? B equals negative A. Okay? So B is negative 1 over root 5. Okay? So we get A and B. Let's replace A and B by these two numbers. We get explicit expression for Fibonacci number. Okay? Yeah. We still use the phi represent that golden ratio number. Okay? Yeah. This one negative 1 over phi. Yeah. Okay? Then let's rewrite this using phi. These two expressions, okay, equals 1 over root 5, positive, negative, right? So then parenthesis that. Okay? In that way, we also find that Fibonacci number formula. This time, we solve a linear recurrence relation. Can you do this kind of calculation? I give you equation with different coefficients. Can you repeat, find the T1, T2 first? Yeah. Find the T1, T2 first. Yeah. So that, so let me